like if we didn't care about logging information, maybe we wouldn't have had this vulnerability. We can move on to the sudo video. Woo! Okay, so first of all, I need to say that I feel a little bit bad about this video because this video, for whatever reason, I accidentally heavily clickbaited, okay? I have to say this thumbnail is pretty good. I'm pretty proud of this thumbnail. Okay, pointers and then zzz and sleeping and so forth. I'm a bit proud of it. And then the title, because this is kind of what this video is about, we just copy some C pointer magic. But I feel like I misled people into thinking that this is some kind of like just pure C pointer video, but it's part of the sudo series because it gets so many views compared to like the performance of this video is better than all my previous videos. Here, check this out. So when you upload a video, Google tells you how well your video performed. And this video is appealing to a wider audience than usual, ranking by view. So within the first 3.5 hours of release, it's ranking first out of 10. It has the most views, has a pretty good click-through rate, but the average view duration is low. So I think I accidentally clickbaited a lot out of this video and people realize, oh shit, that's a boring video, and clicked away again. View duration, 3.5 minutes, sounds low, but I mean, it's lower, a bit less than usual, but not by much less than usual. So it's the average view duration. People always click away. The average view duration of my whole channel is maybe like 4:30 or something. So it's not that much longer. This video is pretty dry. I knew that. That's why I put so much effort into my cool thumbnail. But it's just part of the series. You know, I wanted to share all the different parts of the series, and looking at this pointer loop here that we are looking into now, which is the cause, which is the location of the heap overflow in sudo, is part of the steps you should be doing and have to do. And at the same time, we can step a little bit through assembly and understand a little bit how pointers work. So I try to combine the analysis of the copy loop with maybe a little bit of explanations of pointers. I don't think the video achieved that very well. Like if I would make this video understanding C pointer magic, if that would be the premise of the video, I would kind of do it differently. I think there are better ways how to explain it. I don't know. Whatever. So, yeah. Let's head into it.
We have rediscovered the sudo edit vulnerability in sudo. Our test case actually triggers a malloc abort, and this abort is just a symptom of memory corruption that must have happened in some part of the program earlier. Last video, we already set up an address sanitizer build that helped us identify the location where the actual heap overflow happens. And now we can take this information to look deeper into why this actually happens. The explanation of this is already included in the official Qualys advisory for the bug, but it's sometimes hard to understand it from just a write-up. And also we want to pretend we figured this out ourselves. So let's do the root cause analysis. To analyze the crash we found, it's useful to have a debugged version that makes the process more comfortable. -G is the compiler flag for adding more debug information, so we can ensure to set that by setting the C flags. We can also add -O0 to disable any optimization.
So disabling optimization is really helpful for when you try to understand the assembly code, because things like this copy loop will be more optimized if you don't do that. And assembly can be very easy. Assembly is very basic instruction, right? It's just like move some bytes in this register, increment this register, move it back into somewhere else. So it's like very basic instructions, but if they are optimized, they can be a bit, the patterns are not easily recognizable sometimes, like what exactly is happening. But if you disable optimization, there's like a super clear or fairly clear match between the C code and the assembly code, and it's a bit easier to understand. So for this purpose of understanding this C code better a bit in assembly and so forth, it can make sense to disable optimization. But be aware again that it changes the assembly code. So looking at this copy loop in regular compiled sudo versus the optimized one will look differently in assembly. But again, we are here just to kind of understand what happens even in this loop, and then the non-optimized version can be maybe a bit nicer.
Now let's launch GDB with the source sudo binary. By the way, in this case, I have Jeff installed as a GDB extension for nicer debugging. As we now know from last video, where we used address sanitizer, we learned that the overflow happened in this loop in sudoers.c. Specifically, this memory moving around, writing bytes from into to. And now that we have a debug build, we can actually set a breakpoint based on the file and the code line. Break sudoers.c at line 868. Then we can run it.
Yeah, I break just a little bit before. It should just not break right at that point, but I hope that makes sense.
And we pipe in the minimal crash file as an input. Breakpoint is hit right here at the from to copy.
So again, I'm using Jeff extension, so it provides this very cool output. You see the call stack down here, some information, what's going on. Because it's a debug build and we have the source code available, it can even show you exactly at what line we are at in the C code. And up here you can see the assembly code that is being executed right now, and above that even would be the registers. Here I'm just very zoomed in. So it's obviously very nice output that makes debugging this very nice.
For many of you, this might look like really scary pointer magic. We not only have pointers, but we also mess with them using ++. I know this looks intimidating, but let's look at this in assembly. I know assembly looks even more intimidating, but actually it's much more simple as long as you can read the basic assembly syntax.
I know assembly is not easy, it looks very complex, but assembly has very, very basic instructions, at least for, the standard stuff. Obviously, the Intel assembly has, I don't know, trillions, okay, not that many, different instructions. So it can get very weird, of course, but the basic instructions for your basic programs, it just consists of moves and adds and increments and jumps and compares, and there are just very few instructions that you need to understand how they work, and then you can just sequentially step through it. It's very easy. And I think it's easier to understand sometimes than C code, where you can have brackets and you don't know what will happen first and in what order, and blah. It's very difficult. In assembly, it's easy. Just instruction after instruction after instruction after instruction, and you just, can draw up what's happening. And that's why I understood pointers after I started doing like buffer overflow stuff and looking at assembly. Because once you see pointers in assembly, it makes so much sense compared to any abstract descriptions you get just from looking at C code.
This single line of C compiled to multiple lines of assembly. But don't worry, take my hand and let me walk you through. You will see you could have done that yourself.
Now, I'm not happy with the result, with how I visualized all of this. I feel like it could be easier, but hopefully with my additional commentary now I can make it a bit more understandable what's going on for those that didn't understand. So this is again the Jeff output, and I just put it up into different sections. So up here you can see the command line, but it's not that important. I'm just executing here single steps. It's not that important. This is the important view. It has the assembly code, and the green line is the instruction that we are about to execute next. So we are standing right there, and if we step one forward, we execute this line. Then you can see here the registers. The registers obviously just contain some temporary variables, so to say. And in the bottom right, we see the source code where we are at. So right now we are at exactly this line that we are interested in, these scary pointer assignment, arithmetic, ++ and whatever. So that's basically going on. And now we can step through this. And this is the unfortunate thing. If you watch this in a video, it's very dry, boring. You quickly drift away and you will not understand this. But if you do this once by hand yourself, if you really sit there, step next, you look at the registers and you really think about each line, what is happening, you can also kind of make tests. You can think about what happens in this line. So it loads a value into RAX. Okay, so I expect when I execute this line, RAX should change. So this is kind of like how you can approach this. And if you step through this once, like it's such educational, I think. It doesn't really come across in the video, I think, that well. Okay. RBP is the base pointer. Okay, so now I'm just starting to explain the current situation. So where we are at here, and to understand this line, we are loading with the brackets always means we load from an address something. So we load from an address in RBP minus, so an offset. So here's an address calculated, and from that that's an address, and from that it loads a value. And so to understand this, I just quickly introduce again the stack. The stack is just memory, just continuous memory, it doesn't matter. And a stack frame is defined what is between the base pointer and the stack pointer. Together with the stack pointer, RSP, they define the start and end of a stack frame. So, you know, when we talk stack, we always have this imagination that there's memory that is stacked on top of each other. Obviously, that's not how memory works. Memory is just a huge thing. And RSP and RBP just define these are the two locations. RSP always points at the top of the stack, and RBP is then a bit below that. And together they are the current stack frame. And so here we are loading a value. From RBP, we go a bit minus. Am I confusing myself here right now? So is this loading a value from the previous stack frame? That can't be right? That makes no sense. I don't know. It doesn't matter. See, like these kind of details don't really matter. RBP is larger than RSP. RBP is larger. Right. Yeah, that makes sense. RBP basically could be FFFF, and then we subtract a bit and we go a bit down closer to RSP. Yes, okay, yeah, makes sense. I confused myself. So we are RBP, we do minus hex 48, so we move a bit down, somewhere there is like a local variable. So that's like the most difficult thing kind of to understand here, I think. And local variables are stored on the stack in the stack frame area. So here we are loading the value of a local variable into RAX. Jeff is awesome because it color codes the addresses. This purpley color means. So now you can see we executed this line. So RAX change didn't really change because you know, the same value was in it before already, but we loaded a local variable, and the local variable was an address. And that's a pointer. So we are working here with from. So from is just a pointer, and a pointer is an address. So that's what we loaded now in RAX. It's a stack address. So just from the color, we know these values are stack addresses. And because it's an address, Jeff also tries to check what is stored in that address. And here we apparently have the malicious argument 0000 with the backslash. I get a lot of beginners getting really confused with the outputs of Jeff and PwnDebug. When I started with buffer overflows, I used just GDB, and every time when I wanted to look at the registers, or every time when I wanted to look at memory, I always had to type info registers or examine memory at this register address or whatever, you know. Had to do everything by hand. And by that, it was very conscious decisions what information I want and what was important to me. Now, a lot of people install Jeff right away, and they ask me questions about why certain buffer overflows or things not work, or they don't understand anything. And this output really confuses them because suddenly they get bombarded with information and they don't really understand how to read this information. And so they look at, for example, these values here to the right, and they say, well, there's a string in RAX. And I use that language as well. I would also say in RAX is a string, but that's not really the case. In RAX is a register, it can just hold 64-bit values. So in there is just a string. It's just an address, and that just points, that address is the location where this string is stored. And Jeff is just nice, and it displays us, hey, look, at this location there's a string, and it just displays it in a nice way for us. So we have like the contextual understanding that this points at a string. But yeah, so this can be a bit confusing, but now you know. And that's basically how pointers work. Pointers are addresses, and in RAX we have an address, we have a pointer, and this arrow here is just a perfect symbol because this address points at this value. So RAX is the address location, the pointer where the argument string is stored. And now see what. So this is just logic deduction, right? Like we don't know exactly where this value comes from, but we know the pseudo bug is triggered by an argument where you have 00000 backslash. So this is the argument you used and it shows up here. So I deduct that must be the location of the argument, right? And just by looking at the data itself, you don't need to read that much code. Just in case you are confused, like how do we know that this is the location of the argument? I just simply saw that this looks like my argument. What happens next? We move RAX into RCX. So now we have a copy of the address. And yeah, so now we just execute the things. So we move RAX into RCX. So just we copied that from RAX into RCX. Here again, you can see that GDB is really cool. Every time when an instruction changed a value, it will be highlighted in red. And so this moved the value into RCX. That's why it's now red here at the front, because this was updated. Of course, every time when you execute an instruction, the instruction pointer is also updated, moved to the next instruction. That's why it's also red. So this is very nice to very quickly look only at the registers that were even affected, that even like matter right now. Yeah, and now we come to the next line. We increment RCX, and then we increment RCX by 1. Now look at the C code. Look at the C code. We have a plus plus, which is an increment. So this, matches. You saw now that we incremented this address here. We incremented this pointer. The from pointer was incremented. We took an address and we just added 1 to it. Have a from pointer which is incremented, which means the address is incremented. So we make the address point to the next byte. So RAX is the original address and RCX is the incremented address. And now we write that new incremented value into the same local variable we read earlier from. So we update the variable. And this, so plus plus, if you have used this in programming, it just increments the variable, right? Which means in assembly, you need to load that value, you increment that value, and you write the value back. So this is what happened here. We loaded the value, we incremented it, and we wrote it back. This is what plus plus in C does, right? It increments a variable. So we incremented the from variable. And do you know the difference between plus plus coming before and after the variable? When used within an expression, then the plus plus before and after decides if you take the value and then increment, or if you increment first and then take the incremented value. Plus plus coming after means we first take the value and then increment. But didn't we just increment the variable before using it? Well, technically yes, but we incremented RCX and RAX is still the value before we incremented it. And now from plus plus means, and this is like in C code, you would now have to understand, okay, from plus plus means we use the value first and then afterwards we increment the variable. You don't really have to care about like how to read that really in C. You just look at the assembly. We loaded the value into RAX, then we copied it into RCX, we incremented RCX, we wrote back RCX, but now we keep using the original value. So technically, we have not incremented from yet, or at least the value of from that is now used is the still not incremented one. Yeah, and now we use that to load a single byte into DL, into RDX. Now we use RAX. So the code just already updated the local variable, but we still use now the non-incremented value. For commands to just increment a variable, yes. To be honest with you, I don't know how when you have optimization turned on for assembly, then it might go down to then it will, I don't know, combine a few of the steps into a single step. And then maybe you have like 2 or 3 instructions that kind of correspond to this line here, but yeah. Anyway, RAX still points into our string and we perform a move into DL. I forgot to, when we incremented RCX, you can also see now that it points now obviously to a bit shorter string, right? Like when the 7.2 points at this string, then 7.3 points at the next 0. And that's why this string is now one shorter. Of course, there's like a 0 before it, but this points at the second 0. So that's why it's now a bit shorter. But here we use byte pointer RAX. So this is simply in brackets means we take RAX as an address and we want to move the value stored here. So here we are copying the first byte of this data. So so we copied now the gray line, we just executed that. We copied 1 byte into DL. So we copied the ASCII 0. ASCII 0, the ASCII value is 30. So in the raw byte is 30, but the text representation is a 0. It's ASCII null. In hex 30. So in DL, which is the lowest byte in RDX, you can see now the loaded value hex 30 and ASCII null. So now we evaluated the right part of the equal sign. We loaded a byte from the from pointer and incremented from. And now let's see what the left side is doing. We are starting by loading another local variable, also in RAX again. So here, if you are very observant, you would see that now it's not 4.8 anymore, now it's 4.0. So now we load a different local variable. In this case, of course, it will be the to pointer that we are loading, but essentially it looks exactly the same like the from, right? We have this move RAX with pointer RBP and an offset. So we basically execute the same assembly code as we did for from, because it's essentially the same code, right? We have a to pointer that is incremented. And you can see it's also an address, but this time it's color code. So yeah, we loaded now this local variable, and now the color is different. And as mentioned in the video, Jeff colors the addresses based on to what memory location they belong to. In my color scheme, stack addresses were this purple color and heap addresses were green. So now RAX is pointing into the heap. And here, for example, this information GDB shows us here is a bit useless. So at this location is another address, which points at another address, which points at another address, which maybe I didn't look into it, but could be that this is the linked list of free blocks. So this is a newly allocated heap block, and the first byte should be the next address or pref address or something like that. And yeah, it just you get it. Code is green. This means it's an address located on the heap. So it's a different address pointing. But yeah, the point is that now you should ignore, for example, all of this because that's not interesting to you. We are also writing information to that. So we don't really care what information is there already because we are writing over it now anyway. Does that make sense? Or at least it will come up that we write to that. But yeah, for now we just loaded this value, and now we also copy it into RCX, as you can see here. Somewhere else, but like before, we incremented because the to pointer also has a ++. So we move RAX into RCX, we increment RCX, and we write it back into the local variable on the stack. But again, RAX still contains the address before we incremented it, and see how we use it now. So now we use the non-incremented value, and we write into it the ASCII character we just had. Move the byte we loaded earlier into the location pointed to by RAX. So we are copying this byte onto the heap. And that's it. Yeah, so now we copied it over. And that was the line. We executed now this line. Easy, right? Now you understood this magic pointer line. We simply have two addresses. We dereference the right one to load a byte, and we write it into the location of the to pointer, and we increment both. Executing this in a loop copies bytes. And now let's check the code surrounding this. So we are coming back up now at the start of the while loop, and here is basically the same code we dereference from. So we load a byte from this variable, and that's exactly what happens here in the assembly code. We load into RAX. So see how this assembly line is exactly the same how it was earlier in this assignment down here. Here it's also star from, here's also star from, and you can see that it just loads the local variable into RAX. First local variable, and then we this is just loading from, and star from means you dereference that pointer, so you follow it and do something with that. Down here we copied a byte from that location. That is what the star does. So just from is just loading that address, and then star from is then doing something with the byte that this instruction points to, this address, this pointer points to. And in this case, it's a comparison. So now this address is used in a compare. So at this address, it takes 1 byte and compares it to 0. And this is a 0 check, right? Like you can imagine this is this equal to 0. Unequal to 0. Compare it if the address location is a 0 byte. Strings are null byte terminated in C, so this is simply a loop that checks if we reached that null byte. I was here very worried about people understanding this. Like beginners understanding this, because we are having here ASCII zeros or ASCII nulls, and we talk about 0 bytes. And I know that ASCII and like how bytes and ASCII characters like kind of relate to each other and stuff, it's a bit confusing at the beginning, especially when we talk about an ASCII 0, but then an ASCII byte, because an ASCII, I'm screwing up, an ASCII 0, but a 0 byte, that an ASCII 0 is in fact a hex 30 byte, like it can be confusing. Is this not a null byte? No, it's an ASCII 0 and it's a 30 byte, so yeah, I don't know, can be confusing. And that seems safe, right? We have a loop copying each byte and we copy until we reach the end of the string. All fine, except we have these 2 lines. But here you can also see something really cool. Here we write from bracket 0. Okay, so here, like I said, from bracket 0, but look at the assembly code. The assembly code looks exactly the same like star from, or yeah, like that. And look at the line in assembly. It looks exactly the same like the dereference of the from pointer. It also just loads the address into RAX, and then it loads. So it loads the address on RX, that's like loading from, but now it dereferences it. So the star portion, or in here the bracket 0 portion, takes that address and loads a byte into ECX. So it moves a byte into ECX. It's exactly the same like this from here was down. So the from the copy down here, which shows you that from bracket 0 is equivalent, is the same as writing star from. A byte from that address. It loads a byte like these lines did. In fact, star from and from bracket 0 are exactly the same. This is because arrays in C are also just pointers. So if you load a value from a pointer by dereferencing it, or loading the first value within an array notation, that's the same. Why would you write from instead of star from in this case? And yeah, I think it's, as Yathdi said, it's a matter of taste. It carries like a little bit of different meaning, like if you work with arrays, you can very clearly say the 0th element should be this, then it makes maybe sense to write, the bracket 0. It carries some meaning. To be honest, in this case, I find the meaning a bit misleading. I would have also written here star from. I feel like that's a bit better match in this case because we are modifying from. So we don't see it as a static array where we take the first element, but we modify from. So I would have preferred the star from here, but I mean, that's so like pedantic. I don't know. And so here we check if the current byte is a backslash, and if that is the case, we increment from again. And that is the source of the trouble. Let's see that in action. I have set a breakpoint right here at the copying of bytes, and we can keep continuing in GDB and observe RAX. RAX contains the address of the from pointer, so the source string of the copy loop. And when we just running loop after loop, we keep consuming the source string, copy it into 2 on the heap, and increment the address further. And now we reach the end. We are at the backslash now. And see what happens now. We reach the compare of hex5c, so we check if the byte is a backslash, and that's the case. So now we enter that if case. Here we now increment from. So we load the variable, add 1 to it, and we write it back. Which means the from pointer is now pointing at the... Yeah, we skipped very quickly over it, but this is all known code that we know so far. This line from ++ is loading the variable, incrementing it, and writing it back. pretty much the same stuff that also happened, you know, in the copy loop itself. We load the variable, add 1 to it, and we write it back, which means the from pointer is now pointing at the null byte. You can see here how Jeff does not display a string anymore because a null byte is not a string. It's the end of a string. So this is also maybe a bit confusing. We copied the null byte, and constantly the string, you know, was at the front, the byte that we handle, and now suddenly the null byte is at the end. This is just, you know, a little big endian. I forgot which one we have here, but numbers, you know, the first byte, so to say, is at the end. It's very confusing when you start out. You get used to it at some point, but yeah, so the first byte, so to say, like if you go byte by byte, then this is the first byte is here, the 0 byte. Yeah. So in theory, it's a 0 byte, and then ASCII 000, if you think of it, is a string. But again, a 0 byte is the end of a string. That's why Jeff says, hey, wait, this is not a string. A string is not a null byte. This is not valid ASCII, starting with a null byte. That's why it now displays it as a generic number. A generic value doesn't know what to do with it. Jeff displays it as a hex number now. But here is the null byte. And now we enter the copy line again, and we copy this null byte to the heap, and we increment from, suddenly pointing into another string. Here we also have ASCII zeros, and we keep copying. Yeah, so if you would look at the crashing test case, or if you remember the crashing test case from the previous videos, the crashing test case had so sudo edit -s 00000 backslash, and then the second argument was just a bunch of zeros. So now we are running into the second argument that was, you know, on the command line. The second argument after the first one that had the backslash. So now we are copying that one as well. That now because this while loop check missed the null byte. This if case. Yeah, so this big while loop check, right? This star from that was comparing for a null byte. But we skipped over it because we incremented from with this backslash check here. Here we skip 1 byte forward, and then we skip here the null byte completely. We copy it and then move to the next one, now pointing into the next string. Skipped the null byte. So we copy more bytes than intended. But how many bytes were intended? The to address on the heap where we copied to is coming from user args. And if we scroll up a bit, we can find the place where we allocate the size of the user args. And this size is a sum of all the string lengths of a v, and a v goes over the argv arguments. So we loop over each element of the arguments, we check the string length, and add up the sizes, including the string terminating null byte +1. Yeah, so this makes sense, right? We have a loop that copies arguments. We just saw that, you know, the 0000 backslash and so forth were our arguments. So we have a loop that simply copies arguments. And so it copies it on the heap. And here we allocate, here's the malloc with the size. Here we calculate the size for this allocation, and we loop over all arguments, and we look at the string length of each argument +1 to account for the terminating null byte. So this is the correct size to have enough space to copy all the arguments to, right? Like, this makes sense. And so this here, the size seems to be correctly calculated. So we allocate memory that is large enough to hold all strings. But this loop down here looks for backslashes and skips the value after the backslash, which in theory can only make the string shorter because we skip characters we don't copy, but the bug is that we can skip the final terminating null byte because the backslash is at the end, and thus we skip over it and start copying more data. We skip here into the next string and copy more. So if you have 2 arguments, the first one has the backslash, basically the exact example like we had here, then this first loop will copy, 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 find the backslash, skip over. Oh no, wait, let's start again. So the first takes the first argument. The first argument has the nulls and the backslash. So now it enters the copy loop and it starts copying the null bytes, gets the backslash, it has this condition now, it skips over the null byte, and it keeps copying now the second argument into the location. And when that one is now finished, that one ends at some point, has a null byte at some point, then we go in the for loop to the next argument. Now we come to the real second argument that we want to copy. And now we copy the second argument, but now all the space is already used up. And now actually the second argument will now cause copying and overflowing out of the buffer. More than the string length had calculated earlier. But why is it doing that?
Why is this even looking for a backslash, then skipping it, causing this whole drama? Well, the comment in the code here says, when running a command via a shell, the sudo frontend escapes potential meta characters. We unescape non-characters for sudoers matching and logging purposes. So this is an unescape logic. If you have, for example, an escape double quote, then this copy detects the backslash, skips it, and just copies the double quote. But our backslash was at the end, right before the null byte. So we basically had an escaped null byte and we skipped it.
Security hot take. This whole code only exists for logging purposes. If we didn't have logging, like if we didn't care about logging information, maybe we wouldn't have had this vulnerability.
Cool. Now we understand the copy loop itself and why the buffer allocated a wrong size. The next question we have to answer is, how do we even get here? What conditions need to be set to reach this code, and why does it even care about those backslashes? Let's do a bit more code review next video.
We did it. We got through the boring, dry video. Yeah, so hopefully that made you understand a little bit more of C pointers and stuff like that, and understand the root cause of the heap overflow in sudo. Now, when I did this original, when I worked on this, at this point, I was also obviously interested, why do we have this even? Like, how do we reach this point? Like, why do we need specifically sudo edit and y minus s? Like, why is that the condition where it only works? Why doesn't it work in general with arguments? Why can I just not write sudo and then have a backslash at an argument? So what makes this condition like lead to exactly this spot? And that is what we will focus on next video. So next video we will do a bit more code review of the sudo code to understand better the bug. And then slowly we head into the exploitation part.